Wheels are usually flush with a car's sides, but some cars actually have their wheels falling out the side of the wheelhouses. Some very common examples are off-roaders and American trucks, which I'm not sure what the rest of the world calls them, but in Australia they're also called utes. These cars often have their wheels poking out a little, and even sometimes like 10 centimeters, so like 4 inches. It's quite a lot. So, do poking wheels out of the sides of the car affect the car's aerodynamics? And that is what we're looking at today. And we're looking at it for a couple of reasons. The first one is that one of your amigos wanted to see this, so that's cool. And the second one was that I actually looked into this a little in some experiments, but it was quite a few years ago, and I was in a wind tunnel testing some cars at the time. I had some free time before lunch and I had nothing really to do. I had finished my experiments, played some music, even had a little rave session with some lasers in there. So I was wondering if I moved the wheels out of the wheelhouse so they're poking out a few millimeters, would that do anything to the flow? Actually, I should probably say that don't play around with lasers. They can actually make you go blind. So make sure to always wear safety goggles when you're around them. But I'm an expert, so it's okay. Like at this point, I had about maybe 10 years of experience raving already, so I knew what I was doing. And I got even more experience than that now. So anyway, what I found testing poking wheels out was that it didn't do that much to the drag. And I tested it across a bunch of different rims, from fan rims to completely covered and a lot of different ones in between. And I found pretty much the same thing. But the thing was that I only poked them out a few millimeters, maybe a centimeter at most. And the load cell, the thing that I used to measure the forces, had an uncertainty of about 5 counts in the drag. And this is for a 95% confidence interval. So I was 95% certain that the value that I measured was within the value that the value of the object was within the value I measured, plus or minus 5 counts. And for a normal distribution, 95% confidence interval means a 2 standard deviation spread. And at the end of the day, it doesn't really matter what confidence interval you use, as long as you state what it is in your work. So it might have been that there were some minor changes to the drag to the car, but they were within the 5% uncertainty, so I didn't see them. And at the time, I kind of put it down to the fact that the rear wheels are pretty much in separated flow anyway, so poking them out may not really do too much to the flow. As for the front wheels, well, I kind of figured out that the flow was coming out of them and from the wheelhouses, so perhaps it didn't make much of a difference to poke them out. And coupling that with the uncertainty of the load cell and that the wheels weren't that far out, maybe there wasn't much to see. So I'm really happy to revisit this topic, and to do so, we are looking at a paper called Investigation of Wheelhouse Flow Interaction and the Influence of Lateral Wheel Displacement. It is open access, so you can get a link in the description. And this paper, the researchers did both experiments and CFD, which is always really nice to see. But while this podcast is about how the wheel placement affects aerodynamics, we're actually going to see one of the worst CFD setups I've ever seen published. And what I'm about to say is not nice, but I was actually a little upset when I went through the CFD because, well, you'll see it later on. But I'm just going to say that this CFD was trash. And I'm basing that statement on numbers that I calculated from their data to show this. And I hope that I'm wrong, but I'm going to go through the numbers with you and show you so you can see for yourself. And hopefully I'm wrong, but I'm pretty sure I'm not. But first, let's continue with looking at the wheel location and how that affects aerodynamics, and then we'll get to the CFD later on in good time. So in figure 5, if we scroll down, we can see an experimental setup which is very similar to their setup. So down here, let me zoom in a little bit actually. Here we go. So actually in figure 11, we do see their setup. It's a little harder to see though, because it's like in that kind of opaque kind of view. I'll scroll down to it so we can see what it is. Figure 11 here is their setup, and we have the ground, then the rotating, the wheel drive unit, the wheel, and then the housing, and then like this kind of half bullet shape kind of thing. But it's a little bit hard to see with this figure, so let's go back to figure 5, which is a lot easier to see what's happening here, and I'll zoom in. Maybe that's a little bit too much. Hold on, here we go. Okay, so in fact, figure 5 gives us a good approximation for what we're about to discuss, and it applies to their work. So let's look at this figure because it's a bit clearer. And figure 5 has an idealized car, and it is very similar to the idealized car these researchers used. In fact, it is just the front left quarter of an idealized car, just a front wheel and no rear wheel. So this is one potential limitation of this model, the fact that it only has one front wheel and no rear wheels. Now, in my opinion, I don't think that this is a big limitation to this study, because in my experience, the front and rear wheels don't affect each other very much. Like, you can change the rim designs on the front and rear wheels, and you won't get much of an effect like interaction, and you can change like the rear wheel rims and not the front ones, and you just get like this cumulative effect. So there's not much interaction going on between them. Having said that, I have only really researched real cars and only changing the front and rear wheels and not completely removing the rear wheels. So maybe removing them completely would affect the results, maybe not. Either way, I think we will get a better understanding of how moving the wheels out of the wheelhouse will affect the flow with this paper. However, one thing I do think that makes a big difference between this setup and a real car is that they have only the left side of the car. And I say car in quotation marks because it obviously isn't really a car, it doesn't have rear wheels. But in my opinion, what they have done here, where they have the left side, then put a splitter plate on the right side to effectively make this a symmetry plane, according to potential theory, this is problematic for a car's general aerodynamics. And that is because a car's wake is very transient and actually wobbles around a lot. This is because it is bluff, and we know that bluff bodies have this unsteadiness to it. By only having the left side, you don't really get this unsteadiness. Now this is for a regular car's aerodynamics though, and we are really only interested in the front wheels, which are very far away from the rear of the car anyway. In my experience, I think while it is definitely problematic for the car's aerodynamics in general to have only a quarter car, for what we are looking at with the front wheel, I think it should be fine just to give us an idea as to how putting the wheels in and out of the laterally in and out of the wheelhouse affects the aerodynamics of this section. So I won't say that the exact findings, for example, saying like putting the wheels out 10 millimeters increases the drag by 7 counts. That's not going to be realistic. Like you won't be able to move that to other cars and say that's the same. Even if they had a real car here, you probably wouldn't be able to make that conclusion because they have idealized rims, which we will cover in a second. And there might also be differences between sedans, fastbacks, SUVs, whatever. So having trying to come up with like a very strict amount that it will increase or reduce drag, I don't think is that feasible. So for our purposes, which is to see if poking wheels out have an effect and what kind of effect on aerodynamics, this setup is, I think, pretty fine. So something really cool you can see in figure 5 is this sting holding the front wheel. So this lateral, this horizontal bar coming out into the wheel. That is a way of measuring the force just on the front wheel and decoupling it from the rest of the car. So this is a really cool piece of tech, and decoupling the wheel force from the rest of the car is highly sought after and not commonly done. In fact, when I was interviewing at Mercedes F1, in the interview, the two guys interviewing me asked me how to isolate the wheel forces from the rest of the car and measure them, because at the time that was cutting edge and really important for them. So these researchers moved this wheel up to 20 millimeters out, and they had this decoupling effect going on. Now, they say that they used a 60% scale model. So 20 millimeters on this thing is like 33 millimeters on a regular car. That is quite a lot, but as I said, I have seen some trucks in America that have had their tires out like 10 centimeters. It's a lot. So to know how the wheel's location might affect its aerodynamics, let's first get a good understanding of what a wheel's general aerodynamics is. Now this is actually a really interesting subject and one that I've had the fortune of researching for a while. Now I'm going to say that there isn't really a consensus on the aerodynamics of a wheel, because while everyone can really agree on the major structures, like the jetting vortex, which is the vortex around the side of the wheel, but for the small scale stuff, there is some disagreement and several proposed ideas. And it makes sense that there are different ideas because depending on what car you can have different oncoming flow, the angle of it, how much there is, the speed. Then there is the rim design and the tire design and the housing, and maybe how close the wheels are to the housing, how much it pokes out. These all affect aerodynamics. I don't know. We'll find out in this paper, I guess. Actually, I do know already. And the general rule is the more of the wheelhouse volume the wheel can take up, the less the drag, because the air can't shoot in as much and circulate around as much. But in this paper, we're looking at some other details. So I should actually say now, if you are enjoying this podcast, please subscribe, and because we make new episodes every week, and that is a good way of you not missing out on the goodness coming your way. So in figure 8, which is this figure here, we see one proposed aerodynamic model of the flow around a wheel in a wheelhouse. And it looks pretty good. So we have the L vortex, which is this vortex down here at the bottom near the contact patch. That is the jetting vortex. We have the C vortex that they say comes from the boundary layer separating at the front edge of the wheelhouse, so that vortex here, and then like rolls up a little bit over like the top third of the outside of the wheel. There is the A vortex, which I have also seen here, which is when the flow comes out of the wheelhouse at the top of the wheel. The E vortex, which is down here, going under the rest of the car underbody after being in the wheelhouse. I have also seen this in CFD, but not in experiments because we don't really put probes down there. So I've never really been able to get measurements there. But I have actually taken laser measurements there in this region, so maybe I do have some data on this. I don't know. Anyway, there are also B and S vortices at this rear of the wheel. So the B vortex is around the top of rear of the wheel, and the S vortex is from the flow wrapping around the top rear of the wheelhouse. In my opinion, these two vortices are the most difficult to make sense of because they're very unsteady. Like, for example, I was helping a friend research the pressure fluctuations on the left front door behind, but because of these two vortices, and they wandered around. And we definitely had to have like transient pressure taps for these ones because of how they like moved around. Oh, and I also remembered, I also have done this as well. I've also looked at these vortices on the car. Oh yeah, the problem I had was that I needed to make much finer because I was losing too much information because there were these fine vortices and they were wandering around too much. I couldn't really track where they were going with time. So trying to figure out where they were going in time was really difficult. So that's why I needed a finer grid. Anyway, by comparing the jetting vortex, by comparison, the jetting vortex is way more stable. Like, you know where it's going to be, and it's really easy to identify. So let's move on to their experimental methods. So as we covered earlier, they used a 60% scale model that was just a quarter car. Now the free stream turbulence of this wind tunnel was 0.2%, and it's quite funny because I've always thought that the turbulence density levels of automotive wind tunnels were always way too low. So for example, let's say you're driving along at 100 km per hour, and on that day there's a wind of 10 km per hour and gusts up to 20 km per hour. All of a sudden, you now have like a 10% turbulence density level, not 0.2%. So I can see why having a low turbulence density level is good for research purposes because it reduces potential differences between wind tunnels, but it's not really representative of real life. I always thought that a car should be tested in more an atmospheric wind tunnel where you have a 5% turbulence density level, for example. So one cool thing they did actually was they rotated the wheel, as shown in figure 11, which I'm scrolling to now. Let's go down one more. Okay, here we go. So they've rotated the wheel on this drum, which is fairly standard practice, but often you get some flow bleeding through the gaps around the floor where the drum comes through. So to minimize that, the researchers 3D printed cover plates to cover these gaps. They're the pink bits here. And I don't know, maybe just because they use 3D printing, but I'm impressed. Like, I love 3D printing and anything for 3D printing is cool. And the fact that they used it here is awesome. Now, they say that based on the wheel's diameter, the Reynolds number is 720,000, almost a million, which means that the flow is probably turbulent. In fact, because of the turbulence of this bluff body, that's pretty much a certainty. But also the Reynolds number of the entire idealized car, of this entire idealized car quarter, is like 3.1 millimeters, so 3.1 million, so fully turbulent. They put pressure taps inside the wheel houses, which is always a great idea when working with wheels. They had 114 of them, which is quite a dense grid, and arranged them so that the pressure taps were finer in the regions with higher pressure gradients, which is a really clever thing to do. So they have this pink wheelhouse here, which they show. So they wanted to resolve the regions that changed a lot very well, and that's a very smart thing to do. So the wheelhouse was 140% the width of the wheel itself. So the wheel was centered in the middle, and that means that there was a 20%, as far as I can tell, centered in the middle. So that means there's 20% of the wheel's diameter spacing between the front and back of the wheelhouse and the wheel itself. And the same goes for the top of the wheelhouse. So the wheel was located in there, and there was a 20% gap between the top of the wheel and the wheelhouse. So something that caught my eye was that in figure 11, they show the wheelhouse, but it's not rounded inside. So this inner face here, let's say this is the outer face where the wheel is, this inner face isn't rounded and like sort of quarter spherical. I guess this depends on the car, but generally a sedan-like car will have a rounded inside region, and this is needed for a couple of reasons. The first is that the wheel needs to articulate. So when you turn the steering wheel, obviously the wheel turns. That's how we control the car. So you need to have room for that, for the wheel to be able to rotate around inside the wheelhouse. The second reason why we have this rounding though is that while you could just make a bigger cutout for the wheel to rotate in, remember that the more volume you have, i.e. the volume the wheel doesn't take up, the more drag you will have in the wheelhouse. So by rounding the inside, you provide enough room for the wheel to articulate, but no more in order to reduce the drag. Here, the wheelhouse is just a cut flat surface, and that indicates that you won't have as much of a drag reduction here. Now, they say that the accuracy of the drag coefficient measurements was plus or minus 9 counts. So I'm guessing that is a 95% confidence interval. I'm not sure. I can't see it here, but I'm going to assume that, I guess, that's standard practice. They they write the blockage ratio, but I don't know where, they don't actually mention what it is. So I don't know whether it's like 2%, 5%, I can't find it. So anyway, let's move on. They used PIV and their setup was pretty decent actually. In particular, they took images at 15 Hertz, which while isn't like in the kilohertz range, like the real top end PIV systems, it's quite good and nice to have. I mean, if you have the choice between having a PIV system with 15 Hertz and having one with 14 Hertz, you're going to go for the 15 Hertz one. So that's pretty good. So let's move on to the CFD setup now. So they use the K-Omega SST IDDS approach in Star CCM Plus. This is one that I've also used and it works quite well. It's nice to see that the K-Omega SST terminus model is becoming quite widespread in the automotive aerodynamics industry. All I'm going to say is that when I entered the automotive aerodynamics industry, no one was using the K-Omega SST model and the K-Epsilon model was the standard. But I started using the K-Omega SST model, which I had experienced from aerospace, and I told a few others to use it. And after that, I saw more and more papers from elsewhere reporting it. I'm just saying. So let's move on to the CFD validation, because the route they took to do this is quite different to the conventional way. So the conventional way of validating a CFD simulation, and I use the word validating quite loosely because there are many things that go into it. So the first thing is to look at the mesh independence and time independence convergence studies. And you can say that's not really validation, but it is part of the general process. So this is where you change the mesh and time step to see how that affects your results, and then find values that yield the same results as going finer. At this point, we say that the mesh and time step are fine enough and we don't have to refine them anymore, because if we do refine them anymore, we're going to get the same results, so it's not needed. Then you will usually get some data from elsewhere, and ideally the data you have taken yourself, and then you compare your CFD to see how your CFD lines up with that. So in this study, they skipped the mesh and time step independent studies and went straight to the comparison of the CFD with the experimental results. Is that okay to do? Well, this is where we get into a tricky situation. So the point of the mesh and time step independent studies is to make sure that the grid and time step you are using aren't changing the results from what they should be. So if I were to run a mesh of 5 million cells and the lift and drag or whatever quantity I'm interested in comes out to be the same as a mesh of 10 million cells, then I know that the mesh isn't going to alter my results. But if you have experimental data or real world data, to use the validation that's used in your validating your CFD, do you need to do this? My opinion is that it depends on how much data you have. So if you have a lot, like forces, flow physics across a different range of setups, then I would be okay with using the CFD. I mean, it would be better to do the mesh and time step independent studies because, for example, mesh ensures that you're resolving all of the important vortices and energy containing features in the flow, particularly when it comes to turbulence. But then you can argue that if you have a lot of validation data and your CFD agrees with it, then you have implicitly determined that you have resolved these features adequately. So I'm okay with it as long as the validation data is extensive and covers the range of setups you're going to look at. So that is the route they are taking here, and they are foregoing the mesh independence and time step independent studies and jumping straight to the validation of the experimental data, or with the experimental data, sorry, not of the experimental data, but of the CFD with the experimental data. Now, one thing they are missing out on by not doing independent studies is reducing the number of cells and increasing the time step which they can use without losing accuracy. The benefit of that is to reduce the computational time. So these researchers are more brute forcing their simulations with this approach, but because they aren't simulating too many setups, then this isn't a big loss as what it could really be because they don't do that many simulations. Now, let's look at the validation with their experiments. So the first thing that alarms me is that in tables 3 and 4, they show the effects of the rotating wheel on the lift and drag as they found in the experiments and the CFD. These are given in percentages and they are relative values and not absolute. In other words, from what I can see, they haven't actually given the actual values of the lift and drag coefficients they found in their experiments and or their CFD. I can only see deltas, so differences. I really don't like that approach because all deltas are based on absolute values and these are the values that actually matter. I mean, I can put a beach ball in the CFD simulation and get the same delta in the drag coefficient as a car when you simulate rotating wheels compared to rotating wheels, but that doesn't mean the flow physics around the beach ball is the same, and obviously the beach ball is not the same as the car. And in my experience, when the only validation data is data that is massaged this way, that allows errors to hide in them either by accident or on purpose. So I really don't like this CFD validation so far, but let's move on and discuss what they have found in this validation process. So in the experiments, they found that rotating the wheels reduced the drag coefficient by 5%. On the other hand, the CFD also saw a reduction in the drag coefficient, but it was only 1%. And to be perfectly honest, this is likely within the uncertainty of the CFD simulation. I mean, automotive manufacturers today, they struggle to get their CFD to within 2% accuracy, and they hover more around the 3 to 4% range accuracy. So having a 1% change in the drag coefficient is almost certainly going to be in the error. Or I should say really more the uncertainty. So not only does this CFD not predict the same drag coefficient reduction, it probably doesn't find anything outside the CFD uncertainty either. As for the lift coefficient, the experimental results found a 1% increase, which I think would be within the uncertainty of the experimental setup. The CFD found significantly more at a 4% increase. So this is looking like the CFD isn't really that accurate so far. Let's move on to the flow physics validation. So coming down to figure 13 shows the PIV planes in the experiments on the top two with stationary and rotating wheels respectively, and then the exact same planes in the CFD, stationary and rotating respectively, in the bottom. There are significant differences between the CFD and the experimental results, both for the stationary and rotating wheels. So for example, the weights are much greater in the CFD than the experiments. For example, take this point here. You can see it's like twice as much as for the experiments, and the same kind of thing for the stationary wheels as well. So these are not agreeing. And so I'm going to stop here with the CFD because I'm quite convinced that this CFD isn't accurate enough to look into this topic. I mean, we've seen the force deltas are off, and now the wakes around the wheels are off, and that is going to mean that you can't really capture the effects of poking a wheel out. In addition to all of this, the CFD falls short that they don't give the Y plus as far as I can see. This is an oversight because that goes a long way in telling us whether the KMA SST Thomas model is accurate or not, and at the very least, if their CFD is using wall functions or not. So not including that information is not good. So the rest of this paper, I am not going to look at the CFD. I'm going to concentrate on the experimental results. And fortunately, they did do a good job here, and there's quite a lot of data on the information given on from this side. As for the CFD, right now I would rate it 3 or 4 out of 10. It isn't a pass. It's not good. And for this reason, we are going to and these other reasons that we covered, we are going to ignore the CFD from here on out and just focus on the experiments. And they stated that there is potential error. Actually, one more thing I should mention is that there's also another reason why this CFD may not be accurate. So a couple of reasons actually. One of them is they stated that there is potential error due to the air bleeding through the wheel rotation unit, so the wheel drive units, that they couldn't capture in the CFD. But I also think that there is possibly one more very important thing that they missed out on with their CFD. So let me scroll up actually to these figures. So I couldn't find any information about the tire they used on the wheel, or if they even used the tire, or if they just used the rigid disc. From figure 5, so if we go to figure 5, where is it? Here it is. Figure 5, which isn't their setup, but they said that their setup was very similar to theirs. This had rubber wheels, rubber tires, sorry, from what I can tell. So if they did use a tire, then there are errors in the CFD due to not taking into account how the tire changed shape during rotation. So let's go back to the CFD. Down here, we can see they've got their geometry here, and they haven't factored it into the experiments if they did have it, or the CFD if they had it. So when you rotate a wheel with a tire on it, the tire is made of rubber, so it can flex. And because of the centrifugal force, the tire is being pulled away from the axis of rotation, which means that it is actually expanding a little bit. Also, when you load a tire, there is a bulge at the contact patch. This significantly affects the flow around the bottom side of the tire, because that affects the flow separation and vortex production. So if they used real tires here, or a real tire for this one wheel, then in the simulation, they didn't use that from what I can tell, and they didn't model the effects of this change, and that significantly affects the aerodynamics. At the very least, there should have been a bulge at the contact patch. I mean, I get that the tire stretching is hard to get data on, but the bulge can be done to some extent just through the eye. And yes, real measurements are better, but a bulge of approximately the right size is better than no bulge at all. So let's move on from the CFD and focus solely on experiments. If you want to look at the CFD results, you can still access it in the paper freely in the description below. But now let's go all the way to figure 22, which I'll scroll down quite a bit for that. Down here now. Okay. So in figure 22, in the top two graphs, we see the wheelhouse projection and the calculated drag produced on the faces as you go around the wheelhouses for the stationary and rotating wheels for the experimental results. Now, these are the results between the stationary and rotating wheels, and we don't see much of a difference between the two setups. So in other words, rotating the wheel, while it definitely affects the drag of the car, or the quarter car, it doesn't display much of an effect on the wheelhouse surface, from what I can see. Maybe some minor differences occur at the bottom of the figure, around here maybe, where the rotating wheel reduces the drag a little there, but not much else can be seen. But now we get to the meat and potatoes of the paper, where what we've been waiting for. Here, in table 5, we see how the wheel's location inside the wheelhouse affects the car's aerodynamics. We see the effects of moving the wheel in and out by 10 millimeters. Now they said 20 millimeters at the start, but unfortunately this was just for CFD. So down here, the CFD results are here, when they moved it up to 20 millimeters outside of the wheelhouse. But the experiments don't have 20 millimeters, and we're focusing on experiments now because of the errors. Anyway, when the wheels are stationary, so this top part here, the trend is that the more outside of the wheelhouse the wheels are, the less drag the wheelhouses felt. In fact, if you had the wheel 10 millimeters inside, that produced 6% more drag on the wheelhouse than if you put the wheel 10 millimeters inside, poking out of the wheelhouse, sorry. So in terms of the lift coefficient, I don't know what the percentages are. They didn't give them here. But by poking the stationary wheel out 10 millimeters, as shown in figure 5, sorry, that dropped the lift of the wheelhouse by 38 counts and actually resulted in a downforce of 9 counts overall. A 38 count change is huge just by changing the wheelhouse, the wheel inside the wheelhouse, 20 millimeters. I mean, you can struggle to get that kind of change with something so minor anywhere on the car, except maybe like the diffuser and spoilers. So changing the lateral location of the wheels made a huge difference to the lift and a decent change to the drag coefficient. Now that was for a stationary wheel, and obviously we don't drive around with stationary wheels. Our wheels rotate. So how does changing the lateral location of a rotating wheel affect the wheelhouse aerodynamics? Well, in the same table, this bottom part here, we see that poking the wheels out 10 millimeters from 10 millimeters inside to 10 millimeters outside drops the drag coefficient by 5%. So this value here. So that is a little surprising. Literally poking the wheels out into the flow a little is actually better for the drag coefficient. That is a little counterintuitive, but again, we are kind of in separated flow, so it's not like you're poking the wheel out into really fast moving flow. So maybe that would occur. Now, do you remember actually back how when we were looking at the CFD validation, I was saying how they didn't give the absolute drag coefficient values, just the differences, and that doing that can easily hide major errors. Well, I think I just found a way to show just how bad the CFD was. So in table 6 here, they give the drag data for the CFD of the vehicle with the rotating wheels. Now they give the changes in the drag coefficient, the deltas, when you change how far the wheel is poking out, but they also give the percentage change in the drag. Now, to get the drag coefficient from the drag, you just non-dimensionalize it by the same number. So this percentage difference in the drag is also the percentage difference in the drag coefficient. So because we have the deltas in both the percentage and the absolute values, we can calculate the absolute drag coefficients. Now, from table 6, we can see that an 11 count change in the drag coefficient is equal to an 11 count drag change here is equal to a 3.27 change, 2.7% change in the drag coefficient, and hence the drag as well, the drag and drag coefficient. So factoring that in, we can calculate that the absolute drag coefficient of this car in this kind of configuration is about 336 counts, also 0.336. That is for when the wheel is rotating. So doing the same for the experimental data in table 5, we can see that a 13 count change in the drag coefficient gave a 4.82% change in the drag. That also means that the absolute drag coefficient for the rotating wheel in the experiment was 270 counts, also as 0.27. So that is for the exact same configuration where the wheels went from completely flush to 10 millimeters poking out, that difference between the experiments and CFD results. So the reference areas should almost be identical, except for the tire bulge, which isn't that much more. So their CFD gave a drag coefficient of 0.336. Their experiments gave a drag coefficient of 0.27. That is a 24% difference. Their CFD is wrong by 24%. That is huge. That invalidates their CFD. Now, one more thing that I don't get is that when you calculate the drag coefficient of the experimental car with rotating wheels at 10 millimeters poking out compared to 0 millimeters poking out, you get 270 counts. But if you were to do the exact same thing from 0 millimeters to minus 10 millimeters, we get a drag coefficient of 3,200 counts, so 3.2, which doesn't make sense. So I think that there is an error in the number, probably a typo here for this value. It should be maybe 2.5% maybe. But anyway, from this, we can conclude that their CFD was about 24% wrong and hence never should have been published as it is. Now, as I said at the start of this podcast, if I'd made a mistake, then I'd really be happy to see where. And if you saw one, please let me know in the comments below. But I don't think I have. So that just goes to confirm that what I said earlier, where when you see changes but never absolute values for the quantities you're validating in CFD, that is a major red flag because it is very easy to hide errors with this approach. So that brings us to the end of this podcast. It was a little different than normal because that last finding with the CFD, but I think that we're all in a good place now. So let's end this. And actually, I should say that if you want to get better at CFD yourself, so you can do good simulations and spot errors, like I just did with this paper, check out our CFD courses in the link in the description. Also, we are just about to release our OpenFOAM course. OpenFOAM is a completely free CFD software that is as good as even the big commercial softwares, and in some situations, even better. The problem is that it's quite hard to learn though, especially at first. So our course literally takes you from the very start of how to even install it, all the way to running your own industry-grade simulations with DES, and everything in between like meshing, time-stepping, grid and geometry importing, and all that stuff. We do it in a very easy way to follow, which makes learning OpenFOAM so much easier. And I mean, I wish I actually had this course when I was trying to learn it instead of trying to learn it myself, because learning it myself was so frustrating, and I even gave up a couple of times before finally forcing myself to figure it out after many days and weeks of like not knowing what to do. So you can find that course in the link in the description and make sure to take it, because it also makes you more attractive to potential employers, because you have this major skill that saves them tens of thousands of dollars every year in licensing fees and even training fees for you. So take that course and be a gun at CFD, and I'll see you next podcast. Peace out, amigos.